But uh, he's a specialist in number theory, especially in the areas of modular forms, elliptic curves, and seed theory. But he's recently been working on graph theoretic problems as well. I saw his work on graph polynomials several years ago, I think. But now he's also looking at graph theory and neuroscience. He's also a greatly inspiring speaker, addressing students and teachers on a variety of mathematical themes. It's a great pleasure to have, and also on Indian philosophy, I must add, historical aspects and philosophical aspects. So it's a great pleasure to have Murty with us today. I welcome him to talk to us about graph theory and neuroscience, brain networks. Thank you. Over to you, Ram.
Okay. Well, thank you very much. Let me see if I can share my screen. Is that visible to everybody?
Yes.
Okay. So thank you again for your kind invitation to speak at your Mathematics Teachers Association of India. I'm very honored to be part of the group. So in this talk, I want to talk about, is this visible? Are you able to see the slides now? Okay.
Yes. Yes.
Okay. So the human brain is the final frontier of science, not outer space. It's the inner space. That's in Indian philosophy. We make a distinction between brain, mind, and consciousness, and there are three distinct entities. And the last two are the focus of philosophical inquiry. For example, in the Taittiriya Upanishad, we speak about 5 layers of the human being: the physical body, the Annamaya Kosha, the nervous system, the Pranamaya Kosha, the mental body, Manomaya Kosha, the wisdom body, Vijnanamaya Kosha, and finally pure awareness, Anandamaya Kosha. The first four layers are kind of, in some sense, physical and amenable to research, but the final Anandamaya Kosha is not matter or material. In the Subala Upanishad and many other yoga Upanishads, they speak about 72,000 nerves in the human body. I'm not making this number up. It actually appears. And I just don't know how they would have figured that out, that there are something like 72,000 nerves. There are probably more, but anyway, but that's a big number. And the Upanishad describes these main nerves and their functions. And many of you may not be aware of that. In the 21st century, neuroscience has made significant advances in describing the neural network of the brain. But this work has only just begun. And in this task, graph theory is now the primary tool to describe various aspects of brain connectivity. And there are at least 2 books now in existence talking about brain networks and graph theory. And they're fascinating. They're both written by neuroscience people. And I think it might be a good thing for mathematicians to jump in and try to understand some of the problems that are posed in this field. So my goal in this talk is to give a general introduction to this interdisciplinary theme and discuss some recent work with my neuroscientist colleague, Professor A.N. Prasad. So I will not be assuming any knowledge of either graph theory or neuroscience, so it will be self-contained for a general audience. Now, let me begin by quoting Kant on the mystery of the mind. So here's Immanuel Kant. In the Critique of Practical Reason, Immanuel Kant wrote, "Two things fill me with awe and admiration: the starry heavens above and the moral law within." So, in some sense, the outer space and the inner space, these are the two mysteries that we have. We've been very good at exploring outer space, but when it comes to inner space, we're awfully deficient. So we explored vast tracts of outer space with remarkable technological advances, but when it comes to exploring the inner space of the human mind, we've been quite deficient. And part of the reason is that we've not had the tools to do so. But with the advances in electrophysiological monitoring methods like EEG, we're slowly determining the neural architecture of the brain. And now we can use methods of graph theory to study brain networks, which is in many ways the gateway to the mind. See, the brain network is this pranamaya kosha. So annamaya kosha is the physical body. The pranamaya kosha is the nervous system. The manomaya kosha is the mental body. So at least we can get an understanding of that interface, the gateway to the mind, by studying the pranamaya kosha and how things are connected. So the microscopic structure of the human brain, this first was unraveled by Santiago Ramon y Cajal, a Spanish scientist. He was the first person to begin a serious clinical investigation into the structure of the human brain. And he's credited with the discovery of the neuron. So the neuron here in this picture, you can see parts of the neuron. A neuron is a nerve cell which communicates with other nerve cells through electrochemical impulses transmitted via connections called synapses. And his neuronal theory is considered the foundation of neuroscience. And in a lecture to the Royal Society of London in 1894, he said the ability of neurons to grow in an adult and their power to create new connections can explain learning. So it was only as 1894 that scientists realized some sort of neuronal connection is really at the heart of the learning process. So this being a kind of a conference in education and teaching, in many ways, this particular discovery is relevant. So this is considered to be the basis for the synaptic theory of memory. And Cajal was awarded in 1906 the Nobel Prize in Medicine for this particular discovery. So it's a big achievement in neuroscience. And subsequently, many other neuroscientists developed Cajal's ideas. One of them being Raphael Laurentino, Cajal's student. He advanced the theory that many of the brain functions are emergent functions of the network working in concert. He advanced the theory of recurrent connectivity and showed that nerves transmit electrical impulses. So this is some big discovery again. But remember, I've highlighted the word emergent function. So in science, we try to find the atomic particles, as it were, the basic units which are making everything work. But one of the discoveries of Laurentino is that you may not be able to point to a particular neuron and say this is how this is functioning, but rather a whole bunch of neurons working in concert is giving rise to what we may call the mind or the brain, or that kind of idea. So very much a 21st century idea, especially in the context of the internet, the digital age, where we talk about communication networks and the emergent functions of communication networks. So his work was further developed by Donald Hebb. Here's Donald Hebb, who's Canadian actually, from Nova Scotia. He developed many of these ideas, and Hebb's big discovery is what is called the basic mantra of neuroscience, that neurons that fire together wire together, giving a neurological basis for habit formation and human behavior. So if you keep on doing the same thing again and again, neurons kind of join together, and then you're now caught in this network of neurons, and that's why you keep repeating so on and so forth. Now, this can be used for good or for bad. It explains both of habit formation, whether they're good habits or bad habits. And if we understand the way the neuronal network is working with respect to habit formation, we can make habits and unmake habits by understanding this idea. And Hebb's 1949 book, The Organization of Behavior, is considered as foundational for the development of neuroscience, and many people consider it on par with Darwin's Origin of the Species. Now, the connectivity matrix of the neural networks, this is the word that's used in neuroscience. Instead of talking about adjacency matrix, as what we would normally do in graph theory mathematics, their word is connectivity matrix, because they think each neuron can be represented as a node, and anytime there's a connection, you would you would indicate that by that graph edge. These researchers have now established that brain functions are the outcome of neural assemblies that are connected. So it's a very interesting discovery. And these interconnections can be visualized through the mathematical concept of a graph, where the vertices are either neurons or assemblies of neurons, and the edges are the interconnections between them. Now, the number of neurons is humongous. It's about 10 to the 10 neurons in the human being, and so you're not going to make a vertex for every single neuron. So what people do is they have regions of neuron assemblies, and each of those assemblies then becomes one. For example, when you put an EEG on the scalp or something, you're really only identifying about 50 regions of the brain, and then so each of those regions would be a vertex in the graph. So the adjacency matrix is also called the connectivity matrix in neuroscience. The edges are not undirected but directed, since synaptic connections are not necessarily bidirectional. So it's interesting, isn't it? I mean, I never knew this. It's not bidirectional. Some of these neuronal connections go in only one direction. And in addition, the edges may be weighted to measure the strength of the synapse. So those things, for example, if you're a musician, you're practicing every day playing the keys, you have more synaptic connections with respect to the neurons connected to that motor function, and they are reinforced with every time you practice that. So the strength of that particular synaptic connection is more and is a function of practice. Those things which you're not so very good at, or you're just learning for the first time, the synaptic strength is much weaker. So we're thus left to represent these brain networks as weighted, directed graphs. And so we can study them using methods of graph theory. Now, my neuroscience colleagues were interested in what they call hubs of brain networks. So in other words, supposing you have mapped the brain network, and the question is, where is the action taking place? Where are those areas of the brain where there's more electrical activity? And in that way, they could probably identify these things. So from clinical neuroscience perspective, it's important to identify regions of the brain network where there's more electrical activity. These are called hubs. Several metrics have been introduced to determine hubs, ranging from the naive to the profound. The simplest naive version is what is called degree centrality, in which those nodes with the highest degree play the role of a hub. But of course, we know from graph theory that may not necessarily be the case. Another measure is the betweenness centrality, in which a hub is recognized as a node in which a high percentage of geodesic paths pass through that particular node. Yet another measure is what is called eigenvector centrality, which is closely related to viewing the brain network as a Markov process and is akin to the Google PageRank algorithm. It's this last one that I'm going to focus on in this particular talk, because that's essentially the basis of, at least from my perspective, how we can identify hubs from a complicated network. So how to understand the brain network using graph theory? We know neurons communicate with other neurons and cells via chemical and electrical interactions, and these communications can partially be measured through non-invasive methods such as the EEG or the fMRI and so on and so forth. So an initial model can begin by using graph theory, with the nodes of graphs being either neurons or neuron assemblies, and the weighted directed edges indicating the line of communication along with the strength of the signal. This is what neuroscience is now attempting to do. The Human Connectome Project seeks to map out all the neurons and their connections of the human brain. The work began only 20 years ago and is still in its infancy. So most of you have heard of the Human Genome Project, of trying to map the genetic connections of everything, and so that you understand. Now, in this connection, in this project, what the idea is to identify all the neurons and all the possible connections. So far, we only know the entire neural network of one organism. And this is this poor worm. It's called C. elegans. And it has a grand total of 300 neurons. So all the neurons have been identified. And everything about the worm is known about the neural network, and this is what we tested our particular theory on, and I'll talk about the results at the very end of this talk. So let's begin with the humble origins of graph theory. Graph theory first arose as a form of recreational mathematics, and many trace it to Euler's solution of the famous Königsberg bridge problem. So here's a picture of Euler. You know, Euler's picture, if you notice, his right eye is always kind of closed a little bit or partially closed. It has to do with the fact that he was born with a little deformity, which he suffered through for the whole of his life. So here is the problem, the Königsberg bridge problem. The problem was to walk across each bridge only once and cross all the bridges and return to the starting point. Now, one other form of this problem, as my colleague Vijay Ambakumar has mentioned, is that you don't need to return to the starting point, just cross all the bridges. In any case, however way you interpret it, Euler showed that there's no solution using graph theory. So he modeled the problem as a directed graph, as a graph in this fashion, where each edge is a bridge. So here, this edge here is a bridge, this edge is a bridge, and these are the islands. The vertices are the islands. Each vertex, so if you have to cross a bridge, you can't use the same edge again, so you have to leave by another edge. And this forces an even parity on the degrees of each vertex. And since these vertices have degree 3, there is no solution to the problem. That's more or less the solution that Euler came up with. It requires a little bit of inductive reasoning, but that's more or less the idea. So, as many of you know, a graph is a collection of nodes, sometimes called vertices, edges connecting some or all of them. And the edge can be weighted, and the edges can have a direction. And the most general graph is a directed weighted graph. So here's an example. So here are about 5 vertices, and we have a directed graph. And then each edge is weighted by a certain number. And so we can associate to this thing an adjacency matrix, where each row and each column represents a vertex, and then in the ijth position, we would put the weight of that directed edge. So here, for example, A is connected to B with the weight being 4. Therefore, A in the A-B coordinate, we have 4 here. Similarly, B is connected to C, and therefore in the BC coordinate, we have 3 here. In the CB coordinate, we wouldn't have anything. CB coordinate, we wouldn't have anything because there's no edge going from C to B. So that's how this adjacency matrix works. Now, apart from its intrinsic beauty as a part of pure mathematics, graph theory has been useful in understanding complicated and interconnected processes. They've been used to model communication networks. Here's an example illustrating Indian air routes. So here are all the cities, well, not all the cities, but more those that are connected by air routes. And the cities are the nodes, and they're connected by an edge if there's an air route between them. And you may want to know, how do I get from point A to point B? How fast can I get from point A to point B? Or how cheaply can I get from point A to point B? So one could view it as a weighted graph. We say attach cost of the flight to each edge. And the problem of graph theory is then to get from point A to point B with the minimum cost. Or sometimes you may weight the edge with the time that it takes to get from point A to point B, in which case the problem would be how to get from point A to point B with the minimum amount of time. Now, one way of measuring this issue about getting from point A to point B is using these concepts called radius and radius and the diameter of a graph. As the previous examples show, it is important to determine how fast we can go from point A to point B in any given graph. And one way of measuring this is this concept of radius and diameter. So given 2 nodes, X and Y, we define d of xy as the length of the shortest direct path from X to Y. And the eccentricity of a node is then defined as the maximum distance from X to Y that you can possibly have. And the diameter and the radius of the graph are the maximum and the minimal nodal eccentricities. And it turns out that the brain network is highly connected and the diameter and radius are both small. This phenomenon was rather stunning to neuroscience people, and they often refer to it as the small world phenomenon that you can get from point A to point B. And of course, many of us in graph theory know that there are these sparse graphs, highly connected expander graphs, for example, where the connectivity is very, very good to get from point A to point B, but the number of edges is very small. So the connectivity matrix, so we've already indicated how to attach a matrix to a weighted graph. The most basic matrix to an unweighted, undirected graph is the adjacency matrix, sometimes called the connectivity matrix. And because it's undirected, this matrix is symmetric. And most graph theory texts deal with undirected graphs, and so the adjacency matrices are always symmetric, which simplifies the discussion. So as I already mentioned to you at the beginning, the neuroscience people tell me the synaptic connections may not be bidirectional, that they may only go in one direction. And therefore, you have to go back to basic graph theory and make sure you're not dealing with necessarily symmetric. And that's basically one of the issues that I will discuss in later part of this talk. So here's some examples. So here's some graphs, and all these cases, because they're undirected graphs, you can see the matrices are symmetric matrices. See here, the matrix is symmetric because if you draw the diagonal line here, there's no, it's symmetric about the diagonal. Now, modeling the brain network via graphs. In a brain network, connections are not necessarily bidirectional. We really should be looking at a directed graph. So A is not necessarily symmetric. In our paper, Prasad and I introduced what we call the Markov matrix of a graph, whose XY entry is the reciprocal of the out degree. And now, because we've made the entry to be 1 over the out degree, P is a row stochastic matrix, which means that each row adds up to 1. Now, being a row stochastic matrix means that it has an eigenvalue 1, which is going to come out to be very important at the very end of the talk. The advantage of this perspective is that we can view the graph as describing a Markov process in probability theory. One can view the XY entry as the probability of going from node X to node Y, given that we're currently in node X. And if you are familiar with the topic called spectral graph theory, spectral graph theory has often talked about relating eigenvalues of the adjacency matrix to the properties of the graph. But now it seems in neuroscience and other network theory problems, the Markov matrix is more suited to analyze the graph underlying the brain network, and maybe the spectral theory of the Markov matrix is more important. And that's what we show in our paper. So what's a Markov process? So here's a simple example to illustrate a Markov process. In a certain town, it's observed that if it's sunny today, then there's an 80% chance it'll be sunny tomorrow and 20% chance of rain. I mean, how would you get this information? By observing, tabulating the weather reports over a period of time, let's say over a couple of months or over a year or something, and then you develop, you get this knowledge of statistical knowledge. If it's rainy today, then there's maybe 60% chance of sunshine tomorrow and 40% chance of rain. So you get these things from empirical observations. And having that, we can model this as a two-state Markov process and represent it as a directed graph as follows. So we make two vertices. One is sunny, one is rainy, and the transition of going from sunny to rainy is 20%. The transition from going from sunny to sunny is 80%, so that's the first statement. And then if we're in the rainy state, the transition from going from rainy to sunny is 60%, and the probability of staying in the rainy state is 40%. So you model this in this fashion as a directed graph. So, and then with the matrix, the Markov matrix that you would associate with this graph would be this particular thing. And with P as a transition matrix, the situation 2 days from now is given by P squared, and n days from now is given by P to the n. This is one of the beautiful theorems of Markov theory. So if P models what's going to happen tomorrow, P squared would model what happens in 2 days from now. P cubed will model what happens 3 days from now, and P to the n in general. And then the question as mathematicians we would have is there a limit in eventually where is this going to go? And Markov's theorem is that P to the n actually converges to a matrix limit. And this matrix limit is determined by solving this equation Vp equals V. Notice it's not PV equals V, it's Vp equals V. In other words, V is a left eigenvector with eigenvalue 1. And so Vp equals V is a linear algebra problem. And that once you figure the solution to that particular matrix, once you get a probability vector, then that's the limit. That's according, and once from that you can figure out the limit of the matrix P to the n. This is the basic fundamental theorem of Markov theory. So anytime you have this complicated transition process that you've observed, and you'd like to know where is this going, this is the theorem you would use. Now, as you can see, this has remarkable potential. This baby example of two-state Markov process is only the starting point, but you can see where this could go. Suppose the virus is in this particular mutation today. What is the chance of it mutating into another form tomorrow or another form? What are the possible states it can mutate into? Maybe there may not be one more, there may be 100 more. So then you would have a 100-state Markov process. And then you may want to know in time, where is this work going? And this limit theorem of Markov gives us control. And many of the epidemiologists have been using this model to study the COVID pandemic, for example. So in this particular example, the stationary vector turns out to be 3/4, 1/4, and then what that means in the context of the weather is that it'll be sunny 3/4 of the time and raining 1/4 of the time. So you can see, I mean, this baby example is already potentially powerful to indicate where one could go with this. So Markov's theorem is, and he envisioned a process that can be at any given time in one of m possible states. In the previous example, there were only 2. One could also see that you could have modeled mood swings of an individual from similar happy or sad, and with the transition probabilities encoding the probability of moving from one state to the other. Or you could see more situations where there are not just 2 states, but many states, and then you'd have a matrix which is m by m, depending on the number of states. And Markov's theorem says, I say essentially because there's some conditions, we'll not worry about those conditions, essentially states that P to the n converges to a limit which can be determined by solving this equation Vp equals V. Okay, the jth component of the vector V encodes the probability of the process being in state j at time infinity, and then the final limit of P to the n turns out to be this matrix consisting of all ones, often called J, 1, 1, 1, 1, 1, every entry, times this stationary vector V. Okay, Markov and the philosophy of Markov chains. So let me give you a brief history of how Markov came up with this. So here's a picture of Markov. Here's a picture of Markov and his wife. The theory of Markov chains can thus be described as a mathematical study of recurrence. And Markov started out in number theory, working under the direction of Chebyshev, and his doctoral thesis was about the theory of continued fraction. And if many of you know, continued fractions often is a recurrent process, and you can see how Markov would have come up with this idea of study of recurrence in a more general context, starting from studying continued fractions. I mean, this I find fascinating. Of course, I'm partial to number theory. I find number theory questions, they may sound very theoretical and abstract, but often lead to profound applications in the social context. Now, his thesis was outstanding. He was immediately appointed an extraordinary professor at Petersburg University. His first paper developing the theory of recurrent chains was written in 1906, and it was only 20 years later, in 1926, well after the death of Markov, sadly, that Bernstein saw its importance and gave it the name Markov chains. Now, if we look at Markov's life, it was not a very happy life. For most of his childhood, he used crutches due to a severe inborn deformity of his knee. And at the age of 10, he had an operation on his knee, and afterwards he was able to walk only with a slight limp. And later in life, he developed an aneurysm in his leg, which led to multiple surgeries throughout the years. And one of the operations on his leg was fatal. And on July 20th, 1922, Markov died of sepsis. He was only 66. Now, it's an interesting story that how Markov met his wife, Maria. That's what I think that was her name, Maria. There she is in this picture here in front. And apparently, this is the desk on which Markov came up with this theory of the Markov chains. And his wife was very helpful in writing things up and so on and so forth. It turns out that in those days, women were not allowed to go to school. So the only way rich people could educate their children was to have a tutor come to the house. And Markov, who needed money, being poor, was one of these tutors, and he tutored Maria, and she learned mathematics from him. And then afterwards they got married, and she has always been on his at his side, trying to help him in his work. So this is a kind of an interesting story in itself. Now there is a connection, mathematical genealogy. Let me explain to you the genealogy. Markov's advisor was Chebyshev, as I mentioned in the previous slide. Chebyshev's student was Tamarkin, and Tamarkin's student was D.H. Lamer. D.H. Lamer's student was Harold Stark, and yours truly was Harold Stark's student. So I do have a genealogical connection to Markov, so I'm rather proud of that. You know, in India, what people do is they try to trace their lineage to the great rishis of yesteryears, right? My guru is so-and-so's guru, and so on and so forth. You trace your way back to, you know, Vasishta or Viswamitra or whoever. We do the same in some sense, don't we, in mathematics with this genealogy. In some sense, mathematicians are also sages of sorts. And so I'm kind of proud of this lineage in a connection to Markov. Now, the directed graph is a Markov process. The idea of viewing a directed graph as a Markov process is not new. The Google search algorithm actually does this. But the idea can be used to model many complicated processes, such as the pandemics and the states being the mutations of the virus. And applying Markov's theorem allows us to learn how the virus mutates and gives us a probabilistic understanding of the future states of the virus. Any directed graph can be viewed as a Markov process in the following way. Each node of the graph is viewed as a state. The transition probability from X to Y is 1 over D plus of X, where D plus is the out degree. And this gives rise to what we have described in the previous slides as the Markov matrix of the graph. In this way, we now have two matrices associated with the underlying graph, the connectivity matrix and the Markov matrix. And the spectral theory of both these graphs gives us knowledge of the graph. Now, another important theme that I think we should perhaps develop as mathematicians is the spectral theory of weighted graphs. So that would kind of subsume what I'm saying. You know, normally we only talk about adjacency matrix 0, 1, and so we talk about spectral theory there. But we perhaps should be looking more generally about spectral theory of weighted graphs. The brain network and the brain hubs. It's only last 20 years neuroscience have found the language of graph theory convenient to model the brain neural network of the brain and are using it to study its architecture and functioning. It's becoming increasingly clear the brain has to be studied as a dynamic process of neural interactions between something like 100 billion neurons, which using our directed graph Markov model, we can call as the states. And in this model, the hubs are the regions of the brain with large numbers of connections and are usually situated in the juncture of important fiber pathways, crucial for sufficient network communication. And in neuroscience, such hubs are vulnerable to pathological insults and consequently develop structural alterations that enhance network excitability. Some of my neuroscience colleagues tell me that the brain disorders can perhaps be identified with some lapses in the brain architecture. So they seem to be implicated in many brain disorders, such as epilepsy. So it's important to identify these hubs in the brain network, and this is the background of my collaboration with neuroscientist Professor A.M. Prasad. So the discrete Markov model of the brain network, in the simplest model discussed in the literature, we take nodes I and J of the graph associated to the network, and deem them adjacent if there's a synapse from I to J. That gives rise to a discrete Markov process, and we associate to this graph the transition probability matrix. And if there's no synapse from I to J, we just set the probability to 0. And this is the matrix P that we've been working with. And we confine our attention to brain regions rather than neurons, as I mentioned earlier, as is often done in EEGs. This gives rise to a more manageable graph consisting of about 50 to 100 nodes. And the technical comment is the number of neurons is finite. All neurons are recurrent and non-null, so the fundamental theorem of Markov chains applies. Remember I told you the Markov theorem says P to the n converges to a limit, and there's some technical conditions that need to be imposed before we talk about the existence of the limit. One of them happens to be this comment, and if we have a situation where there are only finitely many states, and they're all, and we can show that they're all recurrent and non-null in the technical sense, I'm not going to explain all of them, then the fundamental theorem of Markov chains applies, and it applies to the neural network. So the theorem is there's a stationary probability distribution V, which is determined by solving VP equals V, and the coordinates of that column vector encode the highest probabilities, and these are the candidates for the brain hubs. Now, the Google search algorithm is doing exactly the same thing. When you type in a keyword in the Google search engine, it goes and finds all the URLs that have that particular keyword, ends up making this directed graph, makes the computation, computes the stationary vector V, and then spits out the search results. And of course, we have very fast algorithms to do these linear algebra calculations. So you may say, oh, it's doing it very fast. Yes, but the algorithm is pretty fast. But the idea behind that algorithm is really this Markov chain process. So we used our interpretation to determine the radius and diameter of the graph. This perspective offers us a new theorem on the radius and the diameter in terms of the Markov matrix. And although the theorem applies to general directed graphs, we will first state it for undirected graphs and indicate the modifications that are needed. So our matrix is a row stochastic matrix. That means all the rows add up to 1. And that translates as that 1 is an eigenvalue, with all the other eigenvalues, non-trivial eigenvalues, having absolute value less than 1. And if you let rho be the maximum absolute value of the non-trivial eigenvalues, then the theorem that we've proved is that if G is an unconnected matrix with the Markov matrix P, which is aperiodic, let's not worry about that for a moment. V is a unique stationary distribution with components VI. The eccentricity of any node then is bounded by log VI over log rho, and the diameter of the graph is bounded by 2 times a maximum of log VI over log rho. What I find interesting about this theorem is how the rho factor comes. This is the absolute value, maximum absolute value of the non-trivial eigenvalues. So very reminiscent of a theme in number theory where the singularity, the main singularity comes into play, and then the other singularities of smaller size go into the error term. In 1989, in a paper in the Journal of the American Math Society, Fan Chung derived bounds for regular graphs in terms of the eigenvalues of the adjacency matrix. And Ramanujam graphs are regular graphs and thus fit into Chung's theorem. But by all indications, the brain network is not a Ramanujam graph, nor is it a regular graph. And so the above theorem seems to be the more appropriate one to use. So this is at least our raison d'etre for writing this paper. The Fan Chung paper would not cover the neuroscience context. And I'm going to flash this because I'm sure not everybody is an expert in this thing, but let me just flash the proof so that the experts that are here can see the main idea. So you have, if it's an undirected graph, you have a real symmetric matrix. And as you all know from basic linear algebra, a real symmetric matrix can be diagonalized. So I can find a matrix C, such as C inverse PC is a diagonal matrix. And the columns of this consist of these orthonormal bases of eigenvectors. And the beautiful thing about diagonalizing this matrix is if I want to compute the nth power of P, then it's just take the nth power of the diagonal entries. And so you have this. So if I want to now get my hands on P to the n, I have just taken powers of this diagonal matrix and I have to multiply on the left by C and on the right by C inverse. And you can see why this is very, very important in the Markov theorem. Remember, Markov was interested in showing where does PLN go? Well, firstly, how do you get your hands on PLN? You get your hands on PLN by diagonalizing the matrix and then using this particular theorem. So PLN now is equal to this. And then if you now try to calculate what is the ijth entry in this on the left-hand side going to, well, it's going to the ijth entry on the right-hand side. And when you write it out, it's like this. And then when you remember the eigenvalues are, one is an eigenvalue, and all the other eigenvalues are strictly less than 1. So you know that if a number is strictly less than 1 in absolute value, the nth power is going to 0. And so the only eigenvalue that matters is the trivial eigenvalue 1, which is going to spit out the main term. This is really what Google is doing. This is exactly what Google is doing. This is basic Markov theory. And so we get, I'm not going to go into all the details, but that's basically the idea. Leave the details. Maybe when I communicate the slides to Ramanujam, people who are interested can look at this thing. And if anyone wants the paper, I would also be happy to send it to them. So you have this kind of limit theorem, which is really amazing. So you see the convergence is, this is going to the main thing. By the way, there should have been an n here. So I have a typo. I do see it. I have a typo here. So Pij to the n is equal to Bj plus Cik lambda k to the power n Bkj, and that's going to 0. Okay. So, and then let's not worry about too much of this, but to get an error estimate, which we need in the main theorem, you need to apply Cauchy-Schwarz and do a little bit of fiddling, which way I will skip. And one of the important ideas to modify this, now I did it only for a real symmetric matrix because I was using the standard theorem of linear algebra that a real symmetric matrix can also always be diagonalized. But if you don't have a symmetric matrix, you can't apply the theorem. And so the two people that came up with a theorem which you can apply are Perron and Frobenius. Here they are. Obviously, this guy lived a long life. Almost 100 years. He lived up to 95. Okay, to treat the directed case, we need this theorem of Perron and Frobenius, which was proved remarkably in 1908. Around the same time, Markov was developing this theory. I find this fascinating because it's some sort of mathematical synchronicity or psychological synchronicity, 2 people, 3 people working on similar things and not really knowing that they're working on the same things. And I'm just going to flash this theorem, the Perron-Frobenius theorem. So there you have a general matrix. It need not be symmetric. And then you can study the eigenvalues, and then you can talk about diagonalizing this thing. And the books that contain this theorem are hard to find. So the one I found is D.R. Cox, The Theory of Stochastic Process, page 120. Another book that I found, which also contains the same thing, is Gantmacher. Gantmacher has 2 volumes called Matrix Theory. I think most of you are probably familiar with that. That book has got wealth of theorems on matrices, and this particular esoteric version is what we need. So, as I say, I'm not going to go into the full detail, but in this context, when the matrix is not symmetric, you can also diagonalize it and then control the eigenvalues in this fashion. Okay, so that's for the experts or technical ideas. And so with using this particular technical version of the theorem, we can extend the theorem to directed graphs. Now, let me get back to that poor worm that I talked about, the 300 neuron worm. This is the only organism from which you have the entire neural network mapped out. This is a roundworm called C. elegans, and it received considerable attention in the literature with the Proceedings of the Royal Society of Biological Sciences dedicating an entire issue to it in 2018. And the connectivity of the matrix of this worm is available online from this website called Dynamic Connectome Lab. And the connection matrix has about 279 nodes linked by 6,393 chemical synapses, 890 electrical junctions, and 1,410 neuromuscular junctions. And, when I looked at this example, the thing that struck me was a famous bhajan of Kabir. Kabir has this remarkable bhajan about what such fine tissue with which, the human being has been created. I forgot exactly the song, but it's a famous bhajan of Kabir. So much delicate work has gone into this fabric of the human, of organisms. And when you look at this, such a worm, we just carelessly sometimes step on a worm. Look at this worm. How many neurons are there? How many connections are there? How much, intricacy in the construction is there? So even such a worm, to study it is very complicated. There's a whole cosmos within this thing. Anyway, we applied our theorem to this worm, and we found that there are only two hubs in this network, what's called PCVL hub and PCVR hub, corresponding to the forward motion. So the first hub corresponds to forward motion of the worm, and the second hub corresponds to reacting to some harsh touch in the tail. So it's even such a simple thing like a worm, but there are only two hubs. These are the two things where lots of electrical activity is going through. So in what to speak, if a worm is so complicated like this, in what to speak of the human being and all the complicated hubs that might be in that network. The continuous time Markov model is probably what we need to use. As you noticed, we use the discrete time model, but really the whole thing is evolving in time. And so if it's evolving in time, you may have to use a continuous time model. And then also I talked about synaptic strength. So you have to probably use functions which reflect the synaptic strength. So how the brain is a complicated network evolving in time seems more appropriate to apply a continuous time model. And the transition probabilities Pxy should be replaced by functions of time. And the matrix P should be replaced by P of T, where it's a function of time. So it's no longer a fixed matrix. So all of a sudden, out goes classical linear algebra, and because the thing is evolving in time. And so the question is whether or not similar theorems can be derived. These functions can measure synaptic strengths. The theory of continuous time Markov chains is a beautiful theory. It's equally elegant, and one can derive a stationary distribution for it as well. And here, so let's try to compress the entire theory of continuous time Markov chains into a few slides. Here you associate a matrix called Q, and this Q is given by these functions Px, y, t in terms of this differentiation process. And so you end up getting these numbers, Qij. So these are now numbers. So starting from a matrix of functions, I got a matrix of numbers, Q. And now we apply the linear algebra problem. Before it was Vp equals V. This time it's Vq equals 0. So Vq equals 0. You solve this using linear algebra, and that determines the stationary distribution of Q. Isn't that amazing? It's a beautiful theorem. It's really a beautiful theorem. So you take this functions of t, and then now you take these transition numbers, solve this problem, and then it goes back, and you can solve continuous time Markov process. So there are various hypotheses that I have, regarding the shape of this function, this matrix P of t. We plan to explore this in future work. Another interesting feature that comes out of our work is what's called the zeta function of a finite network. And what we do is concept of zeta function is familiar to many people, both in graph theory and number theory, as well as algebraic geometry. A similar concept can be introduced in context of neural networks. Indeed, if given any finite directed graph, we can associate this exponential of p to the n to the summation p to the n to the n. It's a matrix again. So the whole thing is a matrix. Our zeta function is a matrix function and resembles zeta functions of number theory in some ways. For instance, the ideas of our paper can be used to show that this particular matrix is really a matrix of rational functions. And it points to the fact, I'm going to make a joke, but anyway, no two people are the same because the zeta functions of their brain networks are different. This is basically the bottom line. So if we meet a person, well, what is the zeta function of your brain network? Well, that's a question we don't know the answer to, but there is such a thing. And it leads to some interesting questions. How are the singularities of the zeta function of the brain net related to the functioning of the brain? This is the domain for future research. Another important thing that seems to emerge from the neuroscience papers is what's called the power law of the brain network. In 2000, Barbassi and Albert noticed many network exhibits of power law in their degree distribution. And more precisely, they noticed that the probability that a random node has degree k is like 1 over kds for some suitable value s. And the brain networks also seem to exhibit such a law. And this is in striking contrast to a random graph, because the random graph exhibits a degree distribution, which is a Poisson distribution. So here, because if these are the probabilities 1 over kds, the probabilities have to add up to 1. So we kind of humorously suggested in our paper that maybe probability x equals k is 1 over zeta s k to the minus s, because the probabilities have to add up to 1 for some suitable s with the zeta s, you know, the Riemann zeta function. So maybe the Riemann zeta function does have something to do with the brain network. Just a partial joke and partial seriousness, but many intriguing questions arise that will be taken up in our future work. So summary of what I've said, we've presented here some new models to identify brain network hubs that may be of use in the treatment of epilepsy and other disorders. Various modalities of measurements are available. It should be possible to clinically test and at least simulate the validity of these hypotheses. Now, much of this stuff, these hypotheses have to be simulated, and fortunately, computer science is there for us. We can model some of these things as a computer simulation. And I think so there's got to be a marriage between mathematics, computer science, and neuroscience, especially in the context of trying to understand this thing. So the study of brain networks using graph theory suggests a retrospective of graph theory from a neuroscience perspective. So you go back to classical graph theory and ask yourself, from the context of neuroscience, how can I use this theorem, or how do I need to modify it in order to use the theorem? As indicated in this talk, this leads to new theorems in classical graph theory in terms of the spectral theory of the Markov matrix. And so this is a new symbiosis between graph theory and neuroscience. So not only can graph theory lead to insights in neuroscience, questions in neuroscience can also lead to new theorems in graph theory, as I've tried to illustrate in this particular talk. So what is the future of brain network research? It seems fitting to conclude this talk with a quote of Olaf Sporns that reflects the interdisciplinary nature of this research. Neither armchair theorizing nor formal mathematical analysis is sufficient to deal with the rich spatio-temporal structure of complex systems. Instead, computer simulations of such systems are necessary to form and test hypotheses to gain mechanistic insight. Without use of computer simulations, it would be impossible to explore complex physical processes as the formation of planets from spinning circumstellar disks of gas and dust, the impact of human activity on climate change, or the folding of proteins. Graph theory will be one of the main disciplines needed to understand the brain. So the brain is indeed the final frontier of science. So thank you for your attention.
So, yeah, thank you very much for that lovely talk, Ram. Looking on chat for there are many remarks, but there is also about the Kabir song that you were referring to. I think, but while people are posting other comments, I want to ask you a question that occurred to me, listening to this.
Oh, I just remember the lyrics of that Kabir song. I think it goes something like, Chini, 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 chini.
So Genie Chadariya, that's what I thought.
So you see, that's a very, you see, the guy got it right, the 15th century.
Yeah.
Very fine, very fine,
Right.
very fine. How did you weave this? How did you weave this? You know, it's this organism. It's such a fine, 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 fine organism. So that's a beautiful song. Anyway, yeah. I just remember the lyrics now. Just that's it.
Yeah.
Okay. So that, another mystery of how the mind works. So why don't we get it at the time we need it? Why do we get it later?
Yeah.
Go ahead.
So, Saurabh, can you please unmute Ambat Vijay Kumar? He has some questions. But meanwhile, while he's waiting, I was wondering whether, see, the thing is that if this way of modeling by graphs, all nodes and edges are identical and homogeneous, right? Now, is that reasonable for brain networks? Because I would have thought that there are multidimensional representations or multi-layers, right? I mean, is it reasonable to make this assumption of all, nodes and edges having the same status?
Yeah, well, that's exactly the point. I think that all nodes and edges are represented, but then where are the major players? In this Markov matrix, and the Markov theorem is going to identify the major players.
I see.
And once you identify them, you can then just focus on those regions.
I see.
That's the idea. Yeah, you're absolutely right. Tiny neuron. You got 10 to the 10 neurons.
Yeah.
Where are you going to identify? So we don't want 10 to the 10. We want maybe 50, 100 regions. Yeah.
So Ram, if I've understood correctly, the neuroscience tells you how the connectivity matrix is formed, right? Because it tells you about the synaptic synapses and the directions and so on and so forth. And then you're using the maths to then figure out which collection of neurons, in a sense, is most important in terms of a hub. So the maths is helping you identify the hubs.
Exactly. Yeah, as it was mentioned to Ramanujam, that exactly 10 to the 10. I think somebody was saying that 10 to the 10 neurons is more than the sand particles in the Sahara Desert. So so where are you going? It's like where are you going to start looking at what are the important points? And that's exactly Markov's thing. Anytime there's a complicated process, not just neurons, but anytime there's a complicated process, there's so many things going on. You'd like to know, where should I look? There's this famous song, "Where do I begin?" Where do you begin? You have to identify the major points to look at. And that's exactly what was going on with viruses or with communication networks or with the internet or something. But this is really the digital age kind of problem of trying to understand the brain networks, because there's just so many neuron players in that network.
Vijay?
I just also wanted to, sorry, very quickly, the paper that you were talking about, Euler's paper, right?
Yeah.
On the original paper is available in English now, and it's really very readable. And I mean, he just explains his thought processes in some sense, and the entire thing is solved using rivers and bridges. Number of bridges on rivers, and he's just looking at naming the bridges using letters and and then looking at the sequence of letters which can occur. And so it's very interesting to read a paper in graph theory without using graphs, in a sense.
Right. Well, at that time, there was no terminology.
Yeah.
In some sense, that was the opening paper where I'm sure he himself thought of it as recreational mathematics as well, and probably didn't realize the potentiality of something. Much of number theory started as recreational mathematics.
Yeah.
So Vijay had a question.
Talk was excellent as usual. I have some remarks to make. Fan Chung has written an article in Bulletin of IMS titled Graph Theory in the Information Age, I think a couple of years ago. That is the first expository article on real world networks in general. During your last time when we met in Cochin talk, I asked you the significance of 1 by d plus. Now I think I have an answer after hearing you again.
Yeah.
I think so. D plus is greater than or equal to 1. So 1 by d plus becomes a fraction, and the matrix has to be stochastic.
Yeah.
So these could be the probabilities attributed to that. That's what I feel now.
Yeah, that's correct. That's correct. Yeah.
And you mentioned that the brain mapping is done for that worm. It has 300 neurons, but as you mentioned, it's not a regular structure. Therefore, the degrees or the synapses connections may be altogether different. That doesn't mean that you will be able to map the brain mapping of some other organisms with that much number of neurons. So that may be a totally different problem.
Yeah.
One good thing that has, or a happy thing that happened in Cochin University after your talk was formation of a research group from members from computer science, physics, electronics, mathematics, and statistics. Okay. We are in fact waiting for Onam vacations to end. We will form the first meeting because there are wonderful experts in biotechnology in our university. So one more information which I want to tell you is that there is a research group in Stanford under Martin Novak who deals with another applications of graph theory, surprising, what we now call evolutionary graph theory, which discusses the Charles Darwin's theory of evolution and the principle of natural selection. So these papers are, I think, 2019-20. And of course, one person cannot read and understand completely the paper. So we need to have an interdisciplinary approach and something like that. So thanks, Ram, for this wonderful talk.
You're welcome.
There is a question on chat from Baba Sharma, who is asking for the non-symmetric case and directed graphs. How does Perron-Frobenius theorem help? Yes, Baba, you want to ask?
Yeah, I think it's clear. You have spelled it out. Yeah, I mean, just in a non-symmetric case, our matrix will not be diagonalizable. I mean, in the sense of, real eigenvalues will not be there. So we'll have lots of complex eigenvalues. So how exactly, this Perron's this theorem is helping? I just wanted to know the ideas.
Yeah, that's a good question. That's a good question. That's exactly the point. The point that now we have a general matrix, and the matrix need not be real symmetric, and therefore the eigenvalues are not real. And in fact, they find that that's the case. But the interesting thing is, under this irreducibility condition, that which is satisfied in the context of the Markov thing, you can diagonalize it. And so it's not going to be a real matrix. You can still diagonalize it, and you can still control the eigenvalues and get that limit theorem. So you see, the limit theorem in the classical context is very easy because you can use standard undergraduate linear algebra. But for this one, you just need this slightly refined version, and you can still get the limit theorem.
Okay, limits will be
the limit will exist, and the main eigenvalue one will be the leading thing. Yeah.
Okay.
I can send you the paper if you want. Just send me an email. I can send you the paper.
Yeah. Okay.
Yeah.
Thank you.
Yeah.
I had a slightly different question, Ram. See, the thing is, the other thing that strikes me with neuronal networks is that they're also dynamic, right? The connections keep breaking and reforming dynamically. And I've seen neuronal time series expansions and so on. So are there any dynamic graph models that are relevant here, or, so that I can also attach probabilities to edges being present at any particular point of time. And, so you've already set up the Markov process. So,
yes. That's a very good question. Yeah, that's a very good question. I think that's exactly where we're supposed to head, because as Hebb's law, the neuronal, neurons that fire together wire together, right?
Yeah,
So,
yeah.
so the more you repeat a certain action, the more habits are formed by these neural, net connections. So if you're going to undo something or learn some new, trick or new ability, in order to cultivate a new ability, you would be reinforcing that thing. And so these neurons will also be evolving in time. So edges will also be evolving in time.
Yeah.
And so that's a good point, and that's where we'll have to go. So as you can see, when we developed, when I say we, I mean we as mathematicians developed a graph theory from a purely mathematical perspective. And I don't think at the very beginning anybody cared about potential applications, because much of graph theory started as recreational math. And as you know, the 4-color conjecture was a big deal. And so people were trying to talk about how many ways can you color a map. And that all looked like recreational mathematics. But eventually, graph theory had potential applications to many so-called real-world problems. And right now, we have that. And so now this is just the beginning. I think the neuroscience thing telling that even the edges are evolving in time. So the graph is evolving in time. Yeah, and that's the kind of math that we would probably have to create.
And also, then stability issues also become very important, right? I mean, then you can also see things very promising and very interesting, I must say. Yeah. And coming to the measures of centrality, which is the sort of thing that you're getting out of the page rank algorithm that you get, right? The measure. So there is a measure of centrality that we are getting. Are there other measures of centrality, and we can see how they are correlated?
Yeah, that's a good question. And that's exactly what this Olaf Sporn's book does. I talked a little bit about it in the slides. I said betweenness centrality, degree centrality. There are other measures of centrality that are important to understanding the brain architecture.
But are they strongly correlated, or?
They may be. I don't think anyone studied the interrelationship between those but they've identified these kinds of centralities. And then at the moment, really the whole subject as I see it, remember, I'm an outsider, I'm not a neuroscientist, but the way I see it, the application of graph theory to neuroscience is really in its baby stage. So what's going on is the neuroscience people have realized this is an important part of mathematics. It's a good tool. So what they've done is they've taken the graph theory theorems as they exist, and they're trying to see what does it say in the neuroscience context. What I'm trying to say in this talk is that we have to kind of go back in the other direction. The neuroscience people want to understand certain things. Maybe you have to revise or enlarge some of the classical theorems and get, so I think it's going to be an exciting time. Yeah.
I believe that. Yeah. What about other questions? Anyone has any comments, questions? Okay. Otherwise, let's thank Murty for this really exciting presentation, showing us very new vistas, starting from extremely simple mathematics to very important contemporary and probably eternal, questions that have been central to human thought for I don't know how long, how many centuries, thousands of years. Yeah, mathematization.
Thank you.
Thank you very much. And over to Jonaki for any remark about tomorrow. And
yes, thank you very much, Professor Ramurthy, for that brilliant talk. For even for people who don't like, for me, it's a completely new thing that you have shared. So, but it's interesting, and I think that even to read about it, even if one is not that familiar with the mathematics, would be very interesting. Thank you very much. And